Welcome to this coding walkthrough. Today, we'll tackle LeetCode problem number 1543, Fix Product Name. This problem focuses on ensuring product names align with a standard format by capitalizing the first letter and normalizing the rest. We'll explore various approaches, analyze their efficiency, and provide an optimized solution. Let's dive in. In this problem, we are tasked with fixing product names that may be inconsistently formatted. The goal is to ensure each product name follows a standard format where the first letter of each word is capitalized, all other letters are lowercase, and words are separated by single spaces. Additionally, there should be no leading or trailing spaces in the output. To achieve this, we will write a function called fixProductName that takes a list of strings, called product_names, and returns a new list with the corrected formatting. The input consists of product names that may have a mix of uppercase and lowercase letters, as well as extra or inconsistent spacing. The output is a list of properly formatted product names that adhere to these rules. Now, let's look at some examples to clarify how the function should work. For instance, given the input list product_names equals Apple iPhone, Samsung Galaxy, Google Pixel, the output should be Apple iPhone, Samsung Galaxy, Google Pixel. Here, we capitalize the first letter of each word, ensure all other letters are lowercase, and remove any extra spaces. Another example is product_names equals MacBook Pro, HP EliteBook, Dell Inspiron, which should produce MacBook Pro, HP EliteBook, Dell Inspiron. Again, the function applies proper capitalization, removes extra spaces, and ensures each word in the product name is separated by a single space. These examples highlight how the function handles different cases of capitalization and spacing. Additionally, we must account for edge cases like empty strings. For example, if the input is product_names equals, the output should be. Here, an empty string remains unchanged as there is nothing to format. This ensures that the function handles even the simplest cases correctly. Notice how the function accommodates various types of input, including strings with inconsistent spacing, mixed capitalization, and even strings that contain no characters at all. By consistently applying the formatting rules, the function ensures that every product name in the output list meets the required standard. Finally, let's consider the constraints and edge cases for this problem. The input list, product_names, can have a length ranging from 1 to 10,000, and each string within the list can have a length ranging from 0 to 100. Strings may contain any combination of lowercase letters, uppercase letters, and spaces. The function must remove all leading and trailing spaces in the output, and words within the product names should always be separated by exactly one space. Edge cases include handling empty strings, strings with only spaces, and strings with inconsistent capitalization. The function should also perform efficiently with large input sizes and be able to handle single-word product names like iPhone correctly. The function signature for implementing this solution is def fixProductName, product_names, list, str-list, str:. To tackle LeetCode problem number 1543, Fix Product Name, we analyzed several approaches aimed at standardizing product names. The goal is to ensure the first letter of each word is capitalized while the rest are converted to lowercase. One approach we considered was the brute force method, which involves manually processing each product name. First, we split the product name into individual words using the split function. Then, for each word, we capitalize the first letter and convert the remaining characters to lowercase. Finally, the words are joined back together with spaces to form the corrected name, and this process is repeated for every item in the list. While this method is straightforward, it has some drawbacks, particularly its inefficiency with large datasets due to the repeated string operations. The time complexity here is n*m, where n is the number of product names, and m is the average length of each name. Additionally, it requires n*m space to store the split words. Although simple, this approach is not the most optimal for scenarios involving large-scale data processing. Another approach we explored is an optimized solution leveraging Python's built-in string library functions. Instead of manually iterating through characters, we can utilize the strtitle function, which is specifically designed for capitalization tasks. This function automatically capitalizes the first letter of each word and converts the remaining characters to lowercase, simplifying the process significantly. The steps involve calling strTitle on each product name, appending the process name to the result list, and then returning the corrected list of names. This method maintains the same time complexity as the brute force approach, O(n*(m), but benefits from the efficiency of pre-built functions, which have been optimized for performance. The space complexity remains O(n*(m) for storing the output list. However, this approach assumes that strTitle can handle all edge cases correctly, such as special characters or mixed casing. Despite this assumption, it provides a cleaner and more efficient way to solve the problem. We also considered an alternative approach based on regular expressions. This method uses regex patterns to identify and transform words directly, offering another way to solve the problem. The process involves defining a regex pattern to match words, such as plus, and then applying transformations to capitalize the first letter and lowercase the remaining portion of each match. Finally, the original word is replaced with its corrected version. The complexity of this approach is also O(n*(m) in terms of time and space, but regex operations can sometimes introduce additional overhead depending on the implementation. While regex is a powerful tool, it can make the code less readable and harder to maintain compared to other methods. After evaluating these options, we decided against the regex approach due to its unnecessary complexity for this particular problem. Instead, we selected the optimized solution using strTitle for its balance of simplicity, efficiency, and readability. In choosing the best approach, we considered several key observations and trade-offs. First, leveraging built-in functions like strTitle simplifies the implementation and makes the code more maintainable compared to manual solutions or regex. While all approaches share the same time complexity of O(n*(m), optimized solutions benefit from lower runtime constants thanks to efficient internal implementations. Additionally, the chosen approach effectively handles edge cases, including mixed casing, empty names, and special characters, ensuring correctness. Ultimately, we selected the optimized approach because it balances simplicity, readability, and performance. By relying on well-tested library functions, we reduce the risk of logical errors and enhance the robustness of the solution. This method avoids the redundancy of manual string manipulation and the complexity of regex, making it the most practical choice for this problem. To solve the problem of formatting a product name correctly, we start by breaking the algorithm down into clear steps. First, we need to validate the input. If the input string is empty, we simply return an empty string as the result, as there's nothing to process. Additionally, we trim any leading or trailing spaces from the input. This ensures that unnecessary whitespace won't interfere with the subsequent steps. Next, we split the input string into individual words using Python's split function. This divides the string into manageable components based on spaces. For instance, if the input is product name, the result of the split operation will be a list containing the words product and name. This prepares the data for processing each word individually. Now that we have the list of words, we iterate through each word to apply the required transformations. For every word, we first check if it's non-empty. This step is important to ensure that we skip over any empty strings that may result from consecutive spaces in the input. For each valid word, we transform its first character to uppercase using word 0.upper, and the remaining characters to lowercase using word 1.lower. We then concatenate these parts to reconstruct the word in the correct format. Once all words are processed, we append them to a new list to store the transformed results. Finally, we use Python's join function to combine these words back into a single string, with a single space separating each word. This ensures that the final output is clean and properly spaced. The reconstructed string is then returned as the result. There are several important insights to note about this algorithm. First, by explicitly converting the first letter of each word to uppercase and the rest to lowercase, we handle all variations of input case sensitivity. This is critical since strings in Python are immutable, so we need to construct a new string for the desired format. Next, the algorithm handles edge cases effectively. For instance, input strings with extra spaces are managed seamlessly because the split function removes these automatically. If the input string is empty, the algorithm efficiently returns an empty string without unnecessary computation. Additionally, single-word inputs are handled naturally, as the split function will still return a list with one element. Lastly, the algorithm is efficient, with a time complexity of O(n), where n is the length of the input string, and a space complexity of O(n), due to the temporary list storing the transformed words. This algorithm relies on two primary data structures. The input and output are both strings, making it highly applicable to text processing tasks. Additionally, we use a temporary list to store the transformed words before reassembling the final string. This simplifies the process of reconstructing the string using the join function. To better understand how the algorithm works, let's consider an example. Suppose the input string is product name. We'll walk through each step of the algorithm to see how it transforms this input into the desired output. Let's break down the example step by step. First, we perform input validation. The input string is not empty, so we proceed. After trimming spaces, the input becomes product name. Next, we split this string into words, resulting in the list, product name. Now, we iterate through each word. For the word product, we capitalize its first letter to get P and convert the rest to lowercase to get product, producing the word product. For the word name, we capitalize the first letter to N and lowercase the rest to AIM, resulting in name. These transformed words are then combined using the join function to produce product name. Finally, the algorithm returns this result as the output. To conclude, let's analyze the complexity of the algorithm. The time complexity is O(n), where n is the length of the input string. This is because each word is processed individually, and operations like splitting and joining the string are also linear in time. The space complexity is O(n) as well, since we store the words temporarily in a list before reconstructing the final string. Together, these efficiencies make the algorithm both practical and scalable for processing product names of various lengths. The provided code is a complete solution to the problem of fixing product names. The goal is to ensure that each word in the input string is properly capitalized, first letter uppercase, the rest lowercase, while removing any leading, trailing, or extra spaces between words. ### line-by-line explanation. 1. Check for empty input. The first step ensures that if the input string is empty, e.g., the function immediately returns an empty string. This prevents unnecessary processing. 2. Normalize whitespace. The strip method removes any leading or trailing spaces from the input string, ensuring clean boundaries. The split method then breaks the string into words based on whitespace. This step also removes extra spaces between words, as split automatically handles multiple consecutive spaces. 3. Capitalize words. Using a list comprehension, each word is transformed to have its first letter uppercase, word 0.upper, and the rest lowercase, word 1.lower. The if word condition ensures that empty strings, if any, are safely ignored during processing. For rejoin words, finally, the transformed words are joined back together into a single string using .join, fixed underscore words, ensuring that words are separated by a single space. ### example execution. Input, hello world. Normalized words, hello world. Fixed words, hello world. Output, hello world. This implementation is efficient, handling edge cases such as empty input, excessive spaces, and mixed capitalization. The time complexity is O(n), where n is the length of the input string, as each character is processed once. The space complexity is also O(n), due to the intermediate list of words. This is the Java implementation of the fixed product name problem, mirroring the logic of the given Python solution. The implementation includes handling empty or null inputs, trimming excess whitespace, and properly capitalizing the first letter of each word while converting the rest to lowercase. Key differences include the use of Java's string builder for efficient string concatenation and explicit type declarations. The logic and behavior remain consistent with the Python version. In this first example, we start with the input string apple juice, which contains extra spaces at the beginning and end. The first step is to check if the input is empty. Since the input is not empty, we proceed to normalize the whitespace. Using the strip function removes any leading and trailing spaces, resulting in apple juice. Then, the split function breaks the string into words, producing the list, apple, juice. Next, we capitalize the first letter of each word. For the word apple, we take the first character, a, convert it to uppercase to get a, and combine it with the rest of the lowercase letters, pli, to form apple. Similarly, for juice, we capitalize the J and keep the rest lowercase, resulting in juice. The updated list becomes apple juice. Finally, we join these words back together using a single space, resulting in the output apple juice. Now, in our second example, the input string is banana split, which is entirely uppercase. Again, the first step is to check for an empty input, and since the input is valid, we move on to normalize the whitespace. Here, there are no leading or trailing spaces, so splitting the string gives the list, banana, split. Next, we process each word to capitalize only the first letter. For banana, we convert the first character, B, to uppercase and the rest of the characters to lowercase, giving us banana. Similarly, for split, we capitalize the S and lowercase the rest, resulting in split. The updated list becomes banana, split. Finally, we join the words together with a single space, resulting in the output banana split. Lastly, we look at an input with mixed casing in just one word, T. After confirming the input is not empty, we normalize the whitespace. Since there are no extra spaces, splitting simply results in the list, T. Now, we process the single word. For T, we take the first letter, T, convert it to uppercase to get T, and then lowercase the rest of the letters, EA, to form T. The updated list contains just T. Finally, we join the words in the list with a single space, which doesn't change the result since there's only one word. The final output is T. In this section, we'll analyze the time complexity of the fixProductName function. First, the function begins by checking if the input string is empty using ifNotName. This operation is a simple conditional check, and it takes constant time, or O1. Next, the strip method is applied to remove any leading or trailing whitespace from the string. This operation scans the string from both ends, and in the worst case, it will process each character exactly once, leading to a time complexity of O(n), where n is the length of the string. Following that, the split method is used to divide the string into words based on spaces. This method also processes each character of the string once, resulting in O(n) time complexity in the worst case. So far, we've seen a sequence of operations that are either O1 or O(n), contributing to the overall time complexity step by step. Now, let's look at the next steps in the function. The list comprehension, word 0.upper plus word 1.lower, for word in words, iterates over each word in the list. For each word, it capitalizes the first letter and converts the rest to lowercase. If there are k words and the average length of a word is m, the time complexity for processing all k words is proportional to k*m. Since the total number of characters in the string, n, is equal to k multiplied by m, this step has a time complexity of O(n). Next, the join method is used to concatenate the words into a single string, adding a space between each word. This operation also processes all n characters in the string, resulting in O(n) time complexity. When we add up the time complexities of all these steps O1, O(n), 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 and O(n), the total time complexity of the function is O(n), meaning the function processes the input string linearly with respect to its length. Now let's evaluate the space complexity of the fixProductName function. The space usage is determined by the memory allocated for intermediate results and the output. First, the input string name is passed as an argument, so no additional space is required for this. Then, the split method creates a list of words. In the worst case, this list contains k words, and the total space required is proportional to the size of the input string, which is O(n). The list comprehension that generates fixed underscore words creates another list of processed words. Since this list also contains k words and has a total size equal to the original string, it requires an additional O(n) space. Finally, the join operation creates a new output string by concatenating the words, requiring O(n) space to store the result. These intermediate lists and the output string are the primary contributors to the function's space usage. Adding up all the space requirements, the function uses O(n) space for intermediate results and the output string. Therefore, the total space complexity of the function is O(n). Comparing this approach to a naive method, a brute force solution might involve manually iterating through the string character by character, identifying word boundaries, and applying capitalization rules. While the time complexity of such an approach would still be O(n), it would likely involve more complex logic and require additional intermediate storage. In contrast, the optimized solution provided here leverages Python's built-in string methods, such as strip, split, and join, which are implemented at the C level for efficiency. These methods streamline the process and ensure that the overall time and space complexities remain O(n). This makes the function both efficient and easy to understand. Finally, let's analyze the best, average, and worst-case scenarios for the function. In the best case, if the input string is empty or very short, the function quickly returns an empty string or processes a small number of characters. Although the time complexity is still O(n), the constant factors involved are minimal. In the average case, for a typical input string with a reasonable number of words, the function processes each character exactly once and maintains an O(n) complexity. In the worst case, where the input string is very long with excessive whitespace or many words, the function still processes each character linearly, keeping the time complexity at O(n). Mathematically, the overall time complexity is dominated by the linear operations of strip, split, join, and the list comprehension, all of which process the string linearly. Similarly, the space complexity is determined by the intermediate lists and the output string, which require O(n) memory. Thus, both the time and space complexities of the function are efficiently maintained at O(n). When working on this problem, there are several common mistakes to watch out for. First, many people assume that product names will always have single spaces between words. This can lead to errors when splitting or joining strings because multiple spaces might exist. To handle this, use split, without any arguments in Python, or the equivalent in your chosen language, as it automatically handles arbitrary spaces. Another frequent issue is neglecting edge cases, such as empty strings or single character inputs like A or A. These cases can cause runtime errors or incorrect outputs if not explicitly checked. It's also important to avoid incorrectly modifying non-alphabetic characters. For example, if the input is 123 apple and you capitalize it as 123 apple, that's incorrect because the numbers shouldn't be altered. Ensure your logic only affects alphabetic characters. Lastly, watch out for inefficient string concatenation. Using loops with plus equals 4 strings has an O(n) squared complexity due to repeated allocations. Instead, you should use efficient methods such as join in Python or string builder in Java, which achieve O(n) complexity. Another common issue is not trimming leading or trailing spaces in the input string. Skipping this step can result in formatting issues or even runtime errors, so always use methods like strip in Python before beginning your main processing. From an interviewing perspective, this problem is an extension of fundamental string manipulation tasks like title casing, so it's important to understand basic operations like splitting, joining, and trimming strings. Interviewers often probe edge case handling, such as how your solution deals with empty strings, numeric inputs, or special characters. Be ready to explain how your logic accommodates these scenarios. Additionally, strive for optimal performance. A good solution should process the string in O(n) time, avoiding nested loops or redundant transformations. Finally, clean, readable code is a priority. Use meaningful variable names and modularize your solution into functions when appropriate, as it demonstrates professionalism and clarity. This problem also connects to several related challenges on LeetCode that can help strengthen your understanding of string manipulation. For example, LeetCode 151, reverse words in a string, involves splitting, trimming, and reconstructing strings, making it a great practice problem. Another is LeetCode 125, valid palindrome, where you need to differentiate between alphabetic and non-alphabetic characters while handling case-insensitive comparisons. Then there's LeetCode 520, detect capital, which focuses solely on capitalization rules, very similar to what we're doing here. Lastly, LeetCode 557, reverse words in a string 3, requires transforming each word in isolation, which is closely related to the title casing logic in this problem. Exploring these challenges can deepen your expertise and prepare you for variations in future interviews. For tackling this problem, there are several alternative approaches, each with its own trade-offs. One option is iterative character-by-character processing. Here, you traverse the string manually, applying capitalization logic when you detect the start of a new word. While this avoids splitting and joining strings, it can lead to a more complex implementation and is best suited for in-place transformations. A simpler approach is to use built-in libraries, such as the title function in Python or capitalize, for individual words. These methods are fast and concise, but they might not handle edge cases, such as non-alphabetic characters or custom rules, without additional tweaks. Finally, there's the regex-based solution. Regular expressions are powerful tools for identifying and transforming patterns in strings. However, while they excel at handling complex scenarios, they can be overkill for simpler problems and may make your code harder to read and maintain. Choose the approach that best balances simplicity, efficiency, and edge case handling for your specific needs. Great job following along. To wrap up, we discussed the importance of string manipulation techniques and handling edge cases for text normalization problems. Remember to balance readability and performance when designing solutions. Thanks for watching, and see you in the next problem walkthrough. Keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!